Today we're going to start Chapter 3. Chapter 3 is about an old familiar friend of ours from previous chemistry classes, stoichiometry. We'll start out here by looking at the origins of the word stoichiometry. Where does stoichiometry come from? It comes from these two Greek words. This one's stoichion, and stoichion means element. Remember, the Greeks believed that there were four elements: earth, wind, fire, and water, and this is their word for element. And then this one here is metron, and this word part shows up in lots of different scientific terms, and it means to measure, or meter is how this is sometimes transliterated to English. So literally what stoichiometry means is element measure. We measure elements in stoichiometry. We measure them by the atom, of course, and by particle groups that are related to atoms. There are two basic kinds of stoichiometry. We're going to first look at composition stoichiometry primarily. Composition stoichiometry is about ratios of atoms of different elements in a compound. This is ratios of atoms in a compound. Like, for example, H2O, very familiar compound. Composition stoichiometry is that branch of science that tells us that there are 2 hydrogens for every 1 oxygen, or in CO2 there are 2 oxygens for every 1 carbon. That's composition stoichiometry. It's concerned with ratios of atoms of elements in a compound. Later on, and you already have some experience with this, we're going to spend a lot more time with reaction stoichiometry, and this is concerned with the ratios of fundamental particles, different kinds of particles. It could be atoms, could be ions, could be molecules, as they are involved in chemical reactions. So, for example, if methane burns in oxygen, we know that carbon dioxide and water will be the 2 products. And this doesn't work out right away. We know that we have to balance this. We've done this before. And when we end up doing that, we have a 2 here and we have a 2 here. So reaction stoichiometry is concerned with the ratios like 2 oxygen molecules for every 1 methane, or 1 methane to 1 carbon dioxide. That's reaction stoichiometry. A real fundamental key term in chemistry is the mole, and this is really the heart of all stoichiometry, is scaling up individual particle measurements to something that's usable. The mole is defined very precisely as the quantity of a substance that contains the same number of particles, so that could be atoms, ions, molecules, as there are atoms in exactly 12 grams of carbon-12. Now, this isn't just some random accidental choice, this carbon-12 and the 12 grams thing. There's some method to it. This number has been given a name. Its name is Avogadro's number, and it's named after Amadeo Avogadro. That's the number of particles that are in 12 grams of carbon-12. And like pi and other numbers, we don't really know what it is, but we do have an estimate. We know it's really large, and it's approximately 6.022 times 10 to the 23rd particles. That's how many atoms, roughly, are in exactly 12 grams of carbon-12. The picture that you're seeing behind the number there on the screen, that's a mole of carbon. So in a quantity that size, there are about 6 times 10 to the 23rd atoms. Moles of different substances are going to take up different sizes depending on the weights of the individual atoms. Stoichiometric ratios, the ratios like 2 hydrogens to 1 oxygen in water, for example, can be expressed in terms of moles as well as atoms or fundamental particles, because every mole contains the same number of particles, which is that Avogadro's number. Here's the beauty of selecting 12 grams of carbon-12 for the definition of a mole. It turns out that the definition of the U, or the atomic mass unit, that's what U is short for, is also defined on the basis of carbon-12. 1/12 of the mass of an atom of carbon-12 is an atomic mass unit. So here's what this does for us. If I take the mass of 1 mole of carbon-12 and I measure it in grams, the number that I get is the same exact number as the weight of 1 atom in atomic mass units, or U's. Same number. And that number for carbon is 12.011. So 12.011 grams is the mass of 1 mole of carbon, And 12.011 U's is the mass of the average carbon atom. It's the same number. Now, where do you find that number? Well, you find that number on the periodic table. Well, here's a periodic table I pulled up on the web. These things are everywhere now. And I'm just going to highlight a few elements. Here's carbon, for example, the one that we were just looking at. If I highlight it, its whole block gets magnified, and we'll take a look at that over here. We can see that carbon is 12.0107. That's the atomic weight. That means that's the mass of the average carbon atom. But it's also what we call the molar mass, the mass of 1 mole of carbon in grams. I use 12.011. They just have a few more sig figs. Let's look at another one, chlorine. Chlorine is 35.453 grams per every mole, but it's also 35.453 atomic mass units per atom. Well, you're familiar with this number, and you've used it before. That's where you get it. Stoichiometric equivalencies, or what we call sometimes mole ratios, are just the fixed ratios of moles or particles, could be atoms or ions, molecules, of one substance to another. Those are called mole ratios, or stoichiometric equivalencies is a kind of a fancier term. These things are useful in dimensional analysis type problem solving. Like using this problem, for example. How many moles of nitrogen atoms are combined with 8.60 moles of oxygen atoms in N2O5? Well, let's solve this problem. I'm going to start out here by writing down my starting point, which is 8.60 moles of oxygen atoms. And my objective here is to find out how many moles of nitrogen atoms does that correspond to. Well, here's what I know. The composition stoichiometry gives me a stoichiometric equivalency, or a mole ratio, that says for every 5 moles of oxygen, there will be 2 moles of nitrogen. It comes right from the formula for the compound. So now I can do my arithmetic, and I know that I'm going to have the right answer because moles of oxygen cancel out, and that leaves me with moles of nitrogen, which is what my answer is supposed to be. And the answer is 3.44 moles of nitrogen. We don't do stoichiometry only with elements. We also can do stoichiometry with compounds. And we may need to find molar masses, or masses per mole, of things that we can't look up on the periodic table. Like this example here, calcium phosphate, Ca3PO4-2. There are 3 elements in this compound, and so to find its molar mass means you're going to have to sum them up. So that's what happens. The mass of a molar mass of a compound is the sum of all the masses of the atoms in the compound. So that would give you the mass of a mole of molecules, or formula units, of the compound. Let's solve this problem. What's the molar mass of Ca3PO4-2, calcium phosphate? So I want to find the molar mass of Ca3PO4-2. What's in there? Well, I'm going to have 3 calcium atoms there, or 3 moles of calcium per mole of calcium phosphate. So I'm going to multiply by the molar mass of calcium, which is 40.08 grams per mole. But I'm going to add to that the molar mass of 2 phosphates. And phosphate includes 1 phosphorus, and there's 2 of them. So 2 times the molar mass of phosphorus. Phosphorus molar mass is 30.97 grams for every mole. But I'm also going to have 8 moles of oxygen, because there are 2 moles of phosphate, and there are 4 moles of oxygen in every phosphate. And oxygen is 15.999 grams per mole. So I'll have to sum this all together to find the molar mass of calcium phosphate. When you add it all up, you get 310.18 grams for every mole. That's the mass of a mole of calcium phosphate formula units. When we're talking about ionic compounds, they are said to have a formula mass because they don't have molecules. So the mass that you calculate, like we did for calcium phosphate, is just the mass of one formula unit, which is the simplest ratio that shows up in a crystal of that compound. Molecular compounds are said to have a molecular mass because it's the mass in U's of one molecule, or the mass in grams of a mole of molecules. But I tend to not distinguish between these two, and I'll just combine these two together with one term, and that term will just be molar mass. So if I say molar mass and I'm talking about an ionic compound, that means formula mass. If I say molar mass and I'm talking about something that's covalently bonded, a molecular compound, then that really means molecular mass. I'll use those interchangeably in this class. How do we convert back and forth? This is going to be very common. You can do this a lot in chemistry. If you have to convert moles to grams or grams to moles, if you have to convert back and forth between these two, your key is molar mass, and the technique that you can use is dimensional analysis. If you have to convert between moles and particles, which could mean atoms, ions, or molecules, back and forth between that and moles, you will use Avogadro's number, and then again the technique is dimensional analysis. Let's try one. How many moles of oxygen are in 25.6 grams of oxygen? Here's how this can be done. Start out by writing down 25.6 grams of oxygen. That's my starting point. What I want to end up with is how many moles of oxygen. Well, I know that oxygen is 15.999 grams per mole. That's just the molar mass. How many grams per 1 mole? By putting the grams on the bottom, I cancel that unit off, and that leaves me with moles of oxygen, which is what I want. My answer is 1.60 moles of oxygen are in that many grams. Here's another one. This is going the other direction. How many atoms of oxygen are in 2.5 times 10 to the third moles of oxygen? Dimensional analysis is again how I'm going to start. I'll write down what I know, 2.5 times 10 to the third moles of oxygen. What I want here in the end is how many atoms of oxygen. Well, here's what Avogadro's number tells me. It's 6.022 times 10 to the 23rd atoms per 1 mole. By putting atoms on top and moles on the bottom, my moles are going to drop out here, and I'll end up with atoms of oxygen. When you do the calculation, you come up with 1.5 times 10 to the 21st atoms of oxygen. So even though it's 2.5 thousandths of a mole, which doesn't seem like much, it's a huge number of atoms because atoms are so small. Gives you an idea of how large a number Avogadro's number is. How many grams of iron are combined with 25.6 grams of oxygen to form Fe2O3? Well, this is a slightly more complicated problem because it's not just a simple conversion. We have to think about stoichiometry here in addition to the conversion. But again, dimensional analysis is the tool I'm going to use. I'll start out with 25.6 grams of oxygen, and then here's what I know. This ratio here of iron to oxygen in this compound formula, that's a mole ratio. So I'm going to have to convert my grams into moles. This is oxygen, so I'll use that molar mass that I used before, 15.999 grams per mole. Now I put the grams on the bottom so that I can cancel them out and eliminate that unit. Now I have moles of oxygen left as units. So I'm going to cancel that away by putting moles of oxygen on the bottom, and I'm going to put moles of iron on the top because I want my answer to come out to be grams of iron. Well, what numbers do I put in here? I look at the chemical formula and I get a stoichiometric equivalency, or a mole ratio. 3 moles of oxygen go with 2 moles of iron. Now, what that does for me is oxygen moles are now canceled out, and I'm left with moles of iron. That's not what I want. I want grams of iron, but I can convert between moles and grams pretty easily. If I look on the periodic table, I find that iron is 55.847 grams per mole. So now that moles cancel out, I have grams of iron. The problem's set up. The only thing I have to do now is arithmetic. The answer comes out to 59.6 grams of iron. You try this one. Stop the video and work out this problem, and then I'll give you an answer in a minute. Well, just like always, we're going to have to start out with what we know in dimensional analysis. So I start with 5.967 grams of water. That's my starting point. Ultimately, somewhere over here, I want to end up with grams of copper. How am I going to get there? Well, a mole ratio is going to be involved here, and it's 5 moles of water for every mole of copper in this formula. So what I'll do is change this into moles. What's the molar mass of water? Well, water has 2 hydrogens in it. If I look on the periodic table, that's 1.008 each. So I'll double that, and then I'll add it to the molar mass of oxygen, which is 15.999. That comes out to 18.015 grams per mole for that compound when I sum up the molar masses of the atoms in it. Grams will now cancel, and now I have moles of water. Here's my ratio: 5 moles of water to 1 mole of copper. Moles of water are now gone, and I have moles of copper. But I want grams of copper, so I'll multiply by molar mass. If I look it up on the periodic table, copper is 63.546 grams for every mole. Moles now cancel, and my answer is going to come out in grams of copper. When I work my answer out, I get 4.210. 4.210 grams of copper are in that compound. Well, I hope this was mostly review for you, and that you're getting back in the swing of doing these stoichiometric calculations. And these simple things like converting back and forth between moles and grams, grams and moles, and then doing these mole ratio things, that's really rudimentary, and you're going to have to do that a lot in this class in the context of more difficult material. So hopefully this is going well so far.